So with that introduction, let's take a look at the first graphic on soil pH. This first graphic is entitled Degrees of Acidity or Alkalinity. You recall I said acid is on the lower end of the pH scale and alkaline is on the upper end of the pH scale. The pH scale is expressed in numerical values from 0 through 14. 7, or the halfway point on the scale, is called neutral. If we have a pH or soil with a pH of 7, that is to say that the hydrogen and hydroxide ion concentration will be the same in that soil. If we have a soil that has a pH of 6 or progressing down the scale below that, this soil is becoming more acidic, which means that the hydrogen ion concentration is increasing at the expense of the hydroxide ion concentration. As we progress up the scale above 7, 8, 9, etc., we are seeing an increase in the OH or hydroxide concentration at the expense of the hydrogen ion concentration. It's not so much about the hydrogen and hydroxide ion concentration as we progress up and down the scale as it is about how that influences the other cations that are held in this soil in a soluble, therefore available and or exchangeable form. To complete the other information that's on this graphic, it shows that distilled water would have a pH of 7. Blood is about 7.2. Milk of magnesia, which is of course taken to offset acidity, is neutral, or not neutral, but above pH or alkaline. Something that we consider quite acidic, like lemon juice, is down there at a pH of about 4. The other thing that we need to understand about this pH scale is that it is a log scale. What that means is that each time we move from one unit to the next on the scale, we are not changing the concentration of hydrogen ions by a factor of 1, but we are changing them by a factor of 10. What this means is that if I have a soil with a pH of 6, 1 unit below neutral on the scale, then a soil with a pH of 6 would be 10 times more acidic than a soil with a pH of 7. If I have a soil with a pH of 5, 2 units below neutral, or pH of 7 on the scale, a soil with a pH of 5 is not 10 plus 10 or 20, but rather it is 10 times 10 or 100 times more acidic than a soil with a pH of 7 or neutral. So the significance of the pH scale being a log scale is that what appears to be a relatively small amount of movement on the scale does cause a significant difference in the actual concentration of ions in soil solution and those held on exchange sites. If I reverse that discussion and moved up the scale, if I went from a pH of 7 to a pH of 8, a soil with a pH of 8 has 10 times fewer hydrogen ions than one with a pH of 7. Correspondingly, a soil with a pH of 9 would be 100 times less hydrogen than one that had a pH of 7. So a log scale implies that a 1 unit move is a 10-fold change in concentration of what we are measuring when we measure the acidity of the soil, which is a concentration of hydrogen ions. Also listed on this graphic says the most desirable growth range, pH range for plants is between 5 and 8. That's a fairly broad range. We have many plants which will be sensitized or sensitive to pHs below 6, like we have some which will be sensitive to pHs above 7. So even though it appears that plants will be not influenced greatly in the pH range of 5 to 8, in essence, most plants grow best between 6.5 and 7.5. So only one unit total length on the pH scale. As we start progressing below 6, many plants are sensitive to those lower or more acidic soil pHs, and certainly as we progress up to 8 and even slightly above, we also see a corresponding decrease in the growth of many plants that are not resistant to these higher pH soils or not favored by growth in these high pH soils.